This is the video for section 3.4 notes, slides 18 and 19. All right, so we are talking about finding the derivative of one more type of function. All right, so we are using what we call logarithmic differentiation for this type of function. So basically, this type of function is when we have some sort of f of x, which is some function u to the v power, right? So what does this mean? We actually are going to have the x's in both the base and in the power. So you recall we had a rule for the derivative. Sorry, u to the v. All right. We had a derivative rule for e to the u. We had a derivative rule for b to the u, right? Where e was the specific constant, approximately 2.718. B was some other constant, any other constant. But now we have u to the v, right? So now both u and v are functions of x. All right, so we cannot use e to the u, b to the u, or we cannot use u to the n. Remember, that was the power rule, right? None of those work because either they only have x's in the power or they only have x's in the base, but they do not have x's in both. All right, so this is what we're going to be doing. All right, step one is to take the natural log of both sides. All right, step two, now remember, this is before taking the derivative. Step one. Step two, simplify both sides using properties of logarithms. All right, so we discussed some properties of logarithms. All right, so we're going to use a few of those. Then we're going to take the derivative of both sides. All right, and then we're going to actually do some algebra. Step four is just algebra. Solve for dy dx. All right, and then number five, substitute in for y. So that'll become more clear when we go through some examples. All right, so that is slide 18. All right, so moving on to slide number 19. All right, so we're just going to use an example here. All right, so find dy dx for y equals x to the 2x. So notice this is x in the base and x in the power. So this is like our u to the v scenario. So we have some function u to some other function v as its power. All right, so first step says to take the natural log of both sides. All right. So I'm going to take the natural log of y equals the natural log of x to the 2x. All right, so that's step one, very simple. All right, step two, simplify using properties of logarithms. All right, so what we're going to do is we're actually going to rewrite the right side. So I'm going to take 2x and bring it in front as a product using the property of logarithms from slide 16. All right, so I have the natural log of y equals 2x times the natural log of x. So now what you should notice here is that I no longer have x in a power. And so I don't need to deal with that anymore. Now I am prepared to take the derivative. All right, so I take the derivative of both sides with respect to x. So d dx of the natural log of y, and then d dx of 2x times the natural log of x. All right, so on the left side, d dx of the natural log of y. So that would be, remember, 1 over y times, don't forget about the chain rule, dy dx equals. On the right side, this is a product, right? So the derivative of 2x natural log of x. All right, so derivative of we take 2x times the derivative of the natural log of x, which is 1 over x, plus the natural log of x times the derivative of 2x, which is 2. All right, now I'm going to leave that alone just for a few moments. All right, so now that is step number 3. All right, step number 4 is to do what? Well, is to solve for dy dx. So how do I solve for dy dx? I multiply by y. So dy dx is going to be y times the quantity 2x times 1 over x plus the natural log of x times 2. All right. Now, I did say I could deal with the right side a little bit, but I'm just actually going to leave it alone for now. And then our last step, step number 5, is to substitute in for y. Now, remember, we were trying to find the derivative of y equals x to the 2x. Well, what is x to the 2x? It's equal to y. So that means down here, dy dx equals y, which is x to the 2x, times the quantity 2x times 1 over x plus the natural log of x times 2. All right, so that is dy dx. Notice dy dx is isolated, all right, and it is entirely a function of x. All right, so now, okay, I don't want you to memorize this, but, okay, how can we generalize this rule? So if I have the derivative with respect to x of u to the v, how can we generalize it? Well, if you look down here, x to the 2x, that was u to the v, and then times the quantity, 2x. What was 2x? That was v times, what was 1 over x? What was 1 over x? Well, it was actually what? 1 over u, but then we would have multiplied by du dx, right? Don't forget about the chain rule. And then plus the natural log of x, so that would have been the natural log of u times the derivative of v, so dv dx. So this would be the generalization, the rule for the derivative with respect to x of u to the v. I do not want you to memorize this, though, because I believe that it's actually easier just to understand the process and to work it out each time rather than to have all those details together. So anyway, so that's slide number 19. All right, so we'll do some more examples in class.